Our next paper here in our series on running biomechanics is Folland et al. 2017, titled Running Technique is an Important Component of Running Economy and Performance. This was, like I said, a 2017 paper, so it wasn't included in the review article from 2016 that we read last time. The review article is typically, that review article specifically, and review articles in general, generally are going to be summarizing a variety of conceptually similar experiments to see if there's kind of general conclusions that can be drawn from the literature as a whole on a particular topic concerning relationships like how does running biomechanics relate to running economy. This study is not a review article. This is what's called in science an original research article, which is, in biomechanics at least, is typically an experiment on human participants, where you'll have participants come into your lab and you'll have them do a certain protocol and measure some performance-related variables and some biomechanics-related variables for the purposes of testing a hypothesis or for examining relationships among variables. Okay. And so that's what they were doing here. This was an experiment on a variety of endurance runners of a range of skill and experience and ability, examining relationships between how they ran, their running biomechanics, and their running economy and their running performance in terms of race time. So a few things I wanted to highlight in this paper. Just for the measurements, for the protocol itself, they talk about a submax test and a max test on the treadmill. Don't worry too much about the max test. That was the part towards the end, I think, of the methods description. And where was that here? Yeah, here where they say after they tested them at a range of speeds on the treadmill, they then did a continuous test where they kind of inched up the speed by 1 kilometer per hour every couple minutes until the subject reported exhaustion. That's the max test here. For that, they were just doing that to try to get an estimate of the VO2 max, of the maximum oxygen consumption that we talked about in the last couple lectures, and that really wasn't a central part of this study, so don't worry about that part too much. The submax tests here are where the guts of this paper came from, and that's where they had the subjects running on a treadmill and measuring their running economy, their energy expenditure during running, and also at that time they were measuring their running kinematics using motion capture. And the submax test here was them running at a variety of submaximal efforts and at a variety of speeds on the treadmill. Now, why did they do a variety of speeds here? Why didn't they just do one speed? Now, remember here, in the past, we had defined running economy as speed versus energy cost of running, or speed versus the oxygen consumed in running. So somebody that has a good running economy, a high running economy at a certain speed, will have a low energy cost of running at that speed. Okay? Now, something you'll often see in biomechanics studies on this topic is that they will often test the running economy or the relationship between running biomechanics and running economy at a range of speeds. They won't just do it at one speed, they'll do it at a variety of speeds. This helps to make the study a little bit more generalizable because runners don't just run at one speed, they run at a variety of speeds. Like if you're doing different types of training or races of different distances, you'll typically do that at a range of different speeds. So testing the running economy at a variety of speeds makes the study a little bit more generalizable, and also in terms of a practical sense, and also for a scientific sense. It helps confirm whether the results or if the results hold across a range of speeds, or if they're just accurate at a specific speed, or if you see categorically different results at different speeds. So all of the results that they report here were averages over a range of speeds at fairly fast running speeds that were still in the aerobic regime, at speeds that would typically be considered aerobic efforts of exercise. Okay, next point I wanted to make was on the sample size and the range of characteristics of the participants. If you scroll from the top here of the paper down to, I think, the third page, at the top of that page you see table 1 here, and this is a pretty common thing that you'll see in original research articles in biomechanics and in science in general, a table here with descriptive characteristics of the participants, just numbers describing who the people were who did the study in a quantitative sense here. One thing to note here is that they had a pretty large number of participants in the study. They had 50 male runners and 47 female runners, so almost 100 participants altogether. That's pretty large for a biomechanics study. I would say the median sample size in biomechanics across all studies is probably somewhere in the range of like 20 participants. So 100 is a pretty large, pretty robust sample size by this typical standards of study design and statistics in biomechanics. You'll see plenty of publications on biomechanics that have far fewer than 100 subjects and far fewer than 20 subjects even. So 100 is, or close to 100 is a pretty good number here. Other thing to highlight here is that if you look at these second two categories of the descriptive characteristics of the participants, or what they call performance and physiology and training, you can see there was a wide range in those characteristics between these participants. In particular here, just to kind of get our feet wet here, if we look at volume, at how much running per week they were doing, averaged across the men and the women, they averaged about 60 kilometers per week, which is in the neighborhood of almost 40 miles of running a week. So on average, these people were pretty serious runners, right? If somebody tells you they run 40 miles a week, like that's somebody that's typically running quite a bit and is taking their running pretty seriously if they're running that much. But also notice here that after they give you the mean and plus or minus the standard deviation for all these variables, in parentheses they also give you the range, and that's where we see just how much variation there was between these participants in their characteristics here. Like on average, people were doing about 40 miles, but the range for the men, for example, was some of them were doing as few as 8 kilometers per week, which is about 5 miles a week. And some of them were doing up to 177 kilometers per week, which is well over 100 miles per week. Okay. So yeah, 40 miles per week on average, but some of them were doing 5 miles, some of them were doing 110 miles. So a great deal of range and of variance there in how much running they were doing. Great deal of variance in how often they were running. Some people doing 2 sessions a week, some people doing 12 sessions a week. And then importantly, quite a bit of range here and variance between these participants in what was their key outcome variable here, the LEC. LEC is what they called the locomotory energy cost, and this was the cost per kilometer of running. So how many calories it costs you to run a mile, for example. So this here is their index of running economy, and it's a little bit different than our index of running economy back here that we've been using previously. This is still a perfectly valid index of running economy, but it's not consistent with our definition that we used back here. So this is the calories per unit distance that you burn when you run. Like if you go out and run a mile, how many calories did you burn? So here we would want a low value of this for somebody to be an economical runner. So the lower your locomotory energy cost here, the lower your LEC in this study, the more economical of a runner you were here. And you can also see, if you look in the parentheses here for that variable, there was quite a bit of variance between subjects and how economical they were. Some subjects were roughly twice as economical as other subjects in this study. Now, is that a good thing? Is that a bad thing? Is it a good thing in a study like this to have a wide range of variance in your key outcome variable here? Typically, for a study like this, I would argue that's a good thing. That gives you a lot of variance to explain and increases, at least in theory, your odds of seeing a compelling result. Let me give you an example of what I'm getting at there. So these are just some data that I made up here in Excel. These aren't actual measurements of human running data. I just made these up as an example. But what you typically do in an experiment like this is you'd have people come into your lab and you'd have them perform some task like running on a treadmill, and you would take some measurement that quantifies how well they performed that task. Like you might measure their energy cost of running or their calories per mile of running. So that would be this F column here. Along with that measurement of how well they did the task, you would also, in this other column, measure some data that you think relates to how they performed the task. So here in column F, how well they performed the task, and here in column E, what they actually did while they were performing that task. So this, for example, would be our energy cost of running, and this, for example, would be our biomechanics that we used while we were consuming that energy. And if I wanted to get kind of a first shot at seeing if maybe there's a relationship between those two things, I could highlight those data. And I can go to Insert Chart and make a scatter plot here. And I get a plot that looks like that, with my biomechanics on the x-axis and my energy cost on the y-axis. And if I just eyeball those data points there, I can say, it looks like the higher the value for this biomechanics variable, the higher the energy cost here. So if I want to pick out the economical runners, it looks like they're going to be the ones that have a low value of that biomechanics variable here. Okay. Now I can formalize that a little bit more statistically rather than just eyeballing those data. I can right-click on my data there and go to Add Trend Line. And we'll stick with a linear trend line. It's the simplest and most common one. And then if I click these two options down here, I say Show or Display Equation on Chart and Display R² value on chart. And then when I click those, you should have seen some text pop up here on my graph. And that's a tiny font. Let's make that a little bit bigger for you guys. Okay, first row here in my text that popped up, that equation there, y equals 1.05-ish times x minus 0.0 or 0.80-ish, that is the equation of this blue dashed line that Excel fit to these blue data points. Okay? So that blue dashed line is called a line of best fit. It's the line that Excel derived by deriving this equation with some statistics under the hood that minimizes the average distance between these blue data points and this blue line. Okay, so that's a line of best fit. It's the equation that Excel says best represents, or from a certain perspective, best predicts those data, in the sense that if I take any arbitrary value of x along this range and plug it into this equation, I can then calculate a value of y that falls on this line and is the prediction of what somebody's, in this case, energy cost, y, would be if they ran with biomechanics x here based on these data. The second and arguably more important part of this line of best fit here is this variable r² at the bottom. R on its own is the correlation coefficient, and it's a measure of basically how well this blue dashed line fits these data points here. The higher, the bigger the value of R there, the stronger the fit here of this line to these data points here. If you take R and then square it, you get a number, R², that ranges from 0 to 1, and that reflects the variance explained. Now, what do I mean variance explained there? You can see here that the data that I made up here has a wide range of values for energy cost and a wide range of values for biomechanics. The higher R² is here, the better my value for biomechanics here is in terms of being a predictor of my energy cost here, or the more variance on my y-axis is explained by my variance on my x-axis. Okay? So R² here can range from 0 to 1. If it's 0, that means none of my variance on my y-axis values is explained by my variance on my x-axis values. Or basically, from this relationship, I wouldn't think that biomechanics relates to economy at all if R² equals 0. If R² equals 1, that means all of my variance on my y-axis is explained by my variance on my x-axis. That's not a case that you'll typically ever get in reality with like human measured data. R² equals 1 would mean all of these blue dots would fall perfectly on this blue dashed line, which you typically won't see something like that in human experiments. But you might see something kind of close to that, like I see here with R² equals 0.9 or 0.95. That would be an indication of a pretty strong correlation, at least in most biomechanics studies, where a lot of my variance, or a lot of my spread in my outcome variable is explained correlationally by variance in my input variable there, by variance in my biomechanics. So this method here, this type of analysis, is called correlation or regression in statistics, and it's the central approach that was used here in this study to examine relationships between running economy and running performance, and running biomechanics. Okay? The actual nitty-gritty minutia of the statistical methods involved is more complicated in reality than this simple example I gave here. But this is kind of the broad strokes of it, the superficial version of the more complicated analysis that they were doing here. Okay, in terms of the actual results of the study, one thing that makes this study a kind of a difficult one to read is that there's a lot of abbreviations in it. And I don't mean to say that this makes it a bad study. This is a really nice study. I actually really like this study. But it does have a lot of abbreviations in it, and it can be difficult to keep track of all of them. And I find myself, when I'm reading this, constantly referring back to this table that they have here somewhere. Yeah, this one here, where it lists all the abbreviations and it explains what they are here and what variable they're referring to. But then they have some that's not in this table here, like VLTP and various other things. And so it can be kind of hard to get through this paper a lot of the time because there's just a lot of abbreviations to keep track of. It doesn't make it a bad paper, but it's just a part of it that's challenging to read for me, at least. So I bring that up as a piece of advice for your own writings and your projects when you're writing your own words in this class. Try not to use lots of abbreviations. Try to minimize the number of abbreviations you use, and only use ones that are really, really necessary, that you feel like you absolutely have to use. If you find yourself using more than, say, just a handful, maybe 3 or 4 abbreviations in your project, that you might try and chop that down a little bit. It can be hard to read if there's lots of abbreviations. Okay, a key one to keep track of here is this locomotory energy cost, LEC. That was, again, their index of running economy. And the lower that locomotory energy cost, the lower your calories per mile is, the more economical of a runner you were. Another one they had here was the lactate turning point. They called that VLTP, or velocity of lactate turning point. This is kind of analogous to that lactate threshold that we talked about a lecture or two ago. This is the velocity of running at which they think you're at what they called your lactate turning point, which means if you were to increase your velocity a little bit, your rate of lactate accumulation in your muscles would start to increase exponentially, and you'd probably exceed your lactate threshold and wouldn't be able to sustain that velocity for too much longer. So this is kind of an index of intensity, and you can also think of this as an index of performance, right? The faster somebody's velocity at their lactate threshold, the faster they can run while still being primarily in an aerobic or mostly aerobic form of exercise. Another one they had here that you again, if you've taken Kines 360, you've probably seen before. If you haven't, it's probably a new one for you, was your respiratory exchange ratio, or RER. This is the ratio between the carbon dioxide that you produce when you breathe over the oxygen that you consume when you breathe. This is generally considered an index, also kind of similar to lactate, an index of intensity of exercise. And so this is something that is looked at to examine intensity. And both of these variables together, these were used to define the speeds, or to choose the speeds that were included in their submax set of tests here. For the submax speeds that they were averaging the results over, they wanted to make sure that these were speeds that were relevant to aerobic type, endurance type running in these participants. So they were mostly using this exchange ratio, and to some extent this velocity at the lactate turning point, just to set the speeds at which they were examining the relationship between running biomechanics and running economy, making sure that that was tested at what they were confident were aerobic type efforts for these participants. Okay, in the results, so what were the actual relationships here between running economy and running biomechanics? The key ones they show here are in figure 2 at the bottom of page 7 of this paper, where here on the y-axis for both of these panels, they're showing your locomotory energy cost. So a lower value here, lower on the y-axis, means more economical. And then on the x-axis were 2 biomechanics variables. Delta Z, P, G, C, comma, H is the vertical oscillations of the pelvis in the stance phase. And VY, P min is the minimum horizontal velocity of the pelvis in the braking phase of ground contact. So what they saw here was that runners that were more economical had smaller vertical oscillations of the pelvis, and also had slower, in an absolute sense, braking velocities of the pelvis in the horizontal direction. So smaller vertical oscillations and slower horizontal velocities in the braking direction during ground contact. Now, let me turn my video on here and give you some demonstrations of those two variables in case they don't intuitively make sense to you, which they may not. So my ground here is going to be my placemat on my kitchen table, and my phone here is going to be my pelvis of my runner. Okay? And as we run, we kind of bounce along the ground from step to step, and our pelvis kind of moves up and down in this kind of oscillatory sinusoidal type pattern here as I take steps and steps and steps across the ground. Okay? So a runner that has small vertical oscillations of the pelvis from step to step might have just this very subtle up and down motion as they run across the ground here, whereas a runner that has large vertical oscillations of the pelvis would have much more dramatic, more pronounced, much more noticeable up and down oscillations of the pelvis. So they saw that runners whose pelvis was moving more like this and not so much like this had the better running economies. So smaller vertical oscillations of the pelvis, better running economies. Okay, the other variable they looked at here was the horizontal, or the minimum horizontal velocity of the pelvis in the braking direction during the ground contact phase. Okay? So let's pretend here that my hand is my foot, and each time that I take a step, each time that I start a ground contact phase, my foot, if I'm a heel striker, first hits the ground like this, and then I roll my foot forward and push off the ground like that. Okay? If you were to look at the ground reaction force produced by that foot motion in the horizontal direction, when my foot first hits the ground like this, notice that my body is going forward to my right here, and then suddenly as it's going forward, it hits the ground and it stops, or at least it slows down. So when I first hit the ground like this, by pressing my foot into the ground, trying to move forward, I'm producing a ground reaction force in the opposite direction. Okay? That force between my feet and the ground in this direction, left on the screen here, is a braking force because it's in the opposite direction. It's opposite my intended direction of progression here. Okay? So if I'm hitting the ground with a forward positive velocity like that, that braking horizontal ground reaction force in this direction is going to slow me down. It's going to make me slower, at least temporarily, in my direction of progression. So what they were trying to get at here with this bottom variable here in this scatter plot was, in the absence of actually measuring those ground reaction forces, trying to get an estimate of how much braking somebody was doing, how much they were slowing down. And they estimated that by looking at, well, what was your fastest velocity in that braking direction? So if you have a more negative value here on this on the x-axis here, that means you had a large fast velocity in the negative direction in the braking phase, which we would probably interpret as a bad thing. At least seems conceptually like it might be a bad thing because it's in the opposite direction. It's a velocity in the opposite direction of the direction that we're trying to run. Whereas if you had a slower or a less negative minimum velocity there for the pelvis in that braking direction, it might indicate that you're not braking as much, you're not slowing down as much, or you're carrying more of your speed forward once you finish that braking phase. And so they saw there that the runners that had the slower maximum or the slower minimum velocities of the pelvis, so the negative braking velocities of the pelvis that were closer to zero here, also had the better running economies, or the lower energy costs of running. They didn't talk about it quite as much, but they didn't have a graph of it, but they also found that there was a relationship between lower energy cost of running and a more extended knee during ground contact, or less knee flexion during ground contact in the runners that were more economical. Okay, so three variables here that kind of kinematically characterize the economical runners. Smaller vertical oscillations of the pelvis, slower minimum braking velocities of the pelvis, and a more extended knee during ground contact. But those three variables altogether only explained about 39% of the variance between all these participants in their energy cost of running. So still a good chunk, still well over half, actually over 60% of the variance in energy costs unexplained here. So not a super strong relationship here between the biomechanics and between the running economy. Last thing that I wanted to highlight here was that if you look in figure 3, is where I'm getting this idea from, there were different sets of, or at least largely different sets of running biomechanics variables that explained the different outcome variables they were looking at. Okay, so here there are kind of three key outcome variables, where this energy cost of running, the LEC, at aerobic type running speeds here. The velocity of lactate threshold, so kind of what's the fastest speed you can run at before you start to accumulate lactate too fast and have to slow down. And then last one here, this is that season's best time from back on table 1 here. And that one, if I scroll back near the top here, back to table 1, that's this row right here, this row SB, the first row, or the first set of data there under performance and physiology, season's best time. This was the participants' best time that they reported in recently in running a 10-kilometer distance. And for some of them, they hadn't run a 10K. They had run some other distance, and they used some methods from the mathy side of track and field to convert it to like an estimated 10K time. But for all the subjects, they had at least an estimated time for how long it would take them to run a 10K. And so that's what they were looking at here back in figure 3 on the right there, their season's best time for running a 10-kilometer distance. So in these bar graphs, the total value of it, the top of the graph, is the fraction of variance in this variable, in this case, energy cost or lactate threshold or season's best time. The fraction of variance in that particular variable explained by the set of running biomechanics that they measured here. Now, each one of these colors that make up that bar graph there is a different biomechanics variable that contributed to that variance explained. And so don't worry too much about the variables themselves, but look at the different colors here, and there's very different sets of biomechanic variables here that were associated, for example, with the energy cost of running versus the velocity of lactate threshold for running. So no consistent set of biomechanics that explained both of those variables, different biomechanics that explained those different variables. The only one that was common here in all three of these, in the energy cost of running, in the lactate threshold, and in the season's best time, was actually that minimum horizontal braking velocity of the pelvis there. So maybe that one is one that is kind of generalizable across a variety of definitions of success or of performance in running. I would argue that the best indicator of performance here among these variables is this one here, the actual performance, right? When we're talking about performance running, this is kind of the nice thing about running. You run faster, you're the better performer. You know, whoever finishes the race first, they're the better performer. It's pretty unambiguous. So if you want to get, real down to the bolts on what's performance, I would say it's this last column here. How fast were you in the race? And so these are the variables there that were associated with that season's best time. Notice here, we do see the same colors there, the same variables explaining the variance in the lactate threshold velocity and in the season's best time for the 10K. Now, this isn't necessarily saying that there's a relationship between these two things. This isn't saying that lactate threshold is important for 10-kilometer racing and energy cost of running is not important for 10-kilometer racing. Actually, I don't think that's too terrible of an assumption to make. I would say your lactate threshold is probably more important for a distance like the 10K than your energy cost of running. But they could both play a role there. But this isn't necessarily showing that there's a relationship between these two things, but it is showing that the variance in them between subjects was explained by a consistent set of biomechanics variables. So maybe something interesting to more closely examine there in future studies, or maybe something interesting to more closely examine why we didn't see a consistent set of variables between all three of these here. Last thing I'll comment on related to what I just said there for this study, then we'll wrap it up for today, was remember that all of these relationships here that I described in this study are between subjects relationships. This is comparing biomechanics between runners who were economical versus runners who were less economical. Okay? So all we can really confirm here, all we can really conclude here is some things on a kinematic signature of economical versus less economical runners. It's risky here to draw any inferences with confidence on what might help somebody be more economical, or how we might train an individual to be more economical. Remember, it's difficult and at best probably a shot in the dark much of the time to take data like this that is between subjects, looking at what's different between different people, and use that to conclude within a specific individual what we should change about them, if anything, to make them more economical. Like, for example, here we saw that the more economical runners had a lower vertical oscillation of the pelvis and a more extended knee and stance and a slower pelvis braking velocity. So does that mean if I take somebody who's an uneconomical runner and train them to run with, say, lower vertical pelvis oscillations, will they necessarily become more economical? Well, no, they won't, right? I can't take these between subjects results and necessarily from that infer a within subject relationship. So this study might give me a compelling motivation for doing a within subject study, like a training study like that, but it's not necessarily going to predict accurately what the results of that study are going to be. So be careful with that when you're reading these different types of studies in the biomechanics literature. Make sure you always keep in mind, is this a between subjects result or is this a within subjects result? One's not necessarily better than the other. I don't want to give you that idea, but they're different designs and you can conclude different things from them. So try not to mix them up. Okay, that is all for today. We will see you next time.